Thanks very much. All right, so today's talk is about the following curve, little n, over the field QP bar. And now here P is a prime, and P doesn't divide n. So capital N is sort of just along for the ride. And now, so the question here is, so by the theorem of Deligne-Mumford, there certainly exists a semi-stable model for this xn. So there exists a script xn, which is smooth and proper, it's a flat proper scheme. And the reduction xn tensor fp has only nodes as singularities, so only nodal singularities. So such a script x certainly exists, and in the appropriate sense it is unique, but our goal today is to actually give a description of one such xn, or at least to give a description of its reduction. So our goal today is to give a description of xn tensor fp bar. All right, so this is our goal for today. And let me just also recap some results on the semi-stable reduction of modular curves before us. So the classical one is that, yes, of course.
Are you going to insist that the special fiber be reduced or not?
Yes, I will. Okay, nodal singularities. Well, this would imply that, wouldn't it? Otherwise, everything's a singularity. You can always kind of clear this up when you pass to a sufficiently ramified. If you add enough roots of unity, you don't have to.
I'm just wondering which convention is going to be.
Oh, there are so many. Yeah, that's right. This is a very weak one. Okay, so we want to give this description. So if the modular curve is x naught of Pn, then the result this has a model by Deligne-Rappaport, whose reduction is this familiar picture of two copies of x naught of n bar. The bar means reduction mod p, and these meet at the supersingular points. So these are nodes. These meet transversely. So this model is semi-stable, and then I mean, if you add more powers of p to the level structure, the results so far are sort of spotty. So if for x equals x naught of p squared n, so this case was done by Edixhoven 90, and then x equals x naught of p cubed n. The result is by Coleman and Ken McMurdy, 2010. And so by this I mean that these authors gave models for those modular curves over ZP bar whose reduction is semi-stable, and the reduction always looks something like this. There are these vertical components, which are like Agusa curves, and then horizontal components, and then the vertical components look something like this. You've got these, first of many oral mistakes I'll be making today. So the supersingular locus, what happens is you take this Katz-Maser model for x of n and do sufficiently many blowups, and you find that you get these vertical components appearing at the supersingular locus. And one thing to remark is that they all pretty much look the same. And the reason for that is that this is really just describing a semi-stable reduction. So each of these vertical configurations represents the semi-stable reduction of the associated deformation space of a supersingular elliptic curve. Curve E, which is something that doesn't really depend on which E there is. You see, they're all isogynous. Okay, and so what we're going to do today is discuss what happens when any power of p divides the level, and discuss the ramifications for the local language correspondence for GL2. And so everything that I do today should have some generalization to the GLN case, although I haven't worked out all the details. The GL2 case, I understand it. Okay, so that was one remark about this. Another remark I'd like to make is that today we're basically just going to be working with curves of infinite level. And so I might talk about things like this, where you have x of p to the infinity. Forget the n for the moment. So such as sort of a tower of modular curves, right? I won't be too precise, but a point of it is a pair e comma alpha up to isogeny, where e is an elliptic curve and alpha is a basis. So if I'll write it this way: alpha is a basis for the rational Tate module Vp of e, right? So yes, so x of p of the infinity is a set of such pairs up to isogeny, And then so it's sort of a simple exercise to see that this is the inverse limit of x of p to the n's. And also you can see from this description that this has an action of GL2QP. So you have an action of the locally compact group GL2QP, whereas at any finite level you can have at best an action of something compact. Okay, so we're going to be working at infinite level, and we're going to be working at the level of deformation spaces of a particular elliptic curve. So far so good? Great. All right. That's basically the last I'll say about modular curves, even though that's in the title. All we talk about from now on is these deformation spaces. In this situation, they're called Lubin-Tate spaces. Okay. All right, so these are deformation spaces of p-divisible groups. Okay. Lubin-Tate spaces. All right, so I'll let. So the object that we deform, which is like this E, is G naught over FP bar, be a p-divisible group, which is formal and dimension 1 over FP bar. And let's call the height h. So the height h, so that'll be greater than 0. And so for instance, when h equals 2, you can let G naught be E of p infinity, where E is a supersingular elliptic curve. All right. And then the Lubin-Tate deformation space so I'll be a little bit sloppy, and I'm not actually going to give a precise definition of it, but I'll say it this way. It's a projective limit of individual rigid spaces mk as k varies through compact open subgroups of GLHQP. And so rather than give a precise definition of each one, I'll just tell you what a point of this M is. So I'll give a definition on the level of points. A point of this M is going to be a triple. Just like a point of x of p to the infinity was a pair like this. A point of M is going to be a triple. Okay. M of, I'll work over CP, is a triple, G and iota and an alpha, and it's all up to isogeny, where G is a p-divisible group, one-dimensional p-divisible formal group over OCP. And iota, well, the iota is going to tell you that G is a deformation of the thing we started with, G naught. So iota is going to be a quasi-isogeny, OCP mod P OCP onto G P of, OCP, P OCP. All right, so it's a quasi-isogeny between G naught and G modulo P. That's right. It's an isomorphism in the category of isogenies where P has been inverted. Okay. And then finally, the alpha is the level structure. And alpha is going to be, it's going to be a basis for the rational Tate module, VP of G. So this is the Tate module tensor QP. Yeah, all right. All right, so a point is given by a triple like this. And there's certainly a relationship between modular curves and Shimura varieties and such Lubin-Tate spaces. One appears as the completion of the rigid space attached to the completion of the other at one of the supersingular points. Okay, so far so good. This is our rigid space. Some observations on it. It's highly symmetric. So M admits an action of a G cross a J. Well, I better not use G. I'll just write it out. G, yes? Oh, sorry. F is QP. I don't know why. Yeah, I really must be careful. OK, everything generalizes to where QP is replaced by a p-adic field F. So that's why I wrote F. So I have to be careful about this. So M admits an action by GLH of QP cross a group I'll call J. and the action of GLHQP. So an element here knows how to operate on alphas. And what is this J? So if I let B be the endomorphism algebra up to isogenies of the G naught, then this over QP. This is a division algebra of invariant 1 over H over QP. And let's just have J be B cross. It's a twist of GLH over QP. And how does this operate? Well, I mean, it operates on the quasi-isogeny iota. You can precompose with an element of this J. All right, so it's highly symmetric this way. And in fact, so this is this theorem of Harris and Taylor, which is that the cohomology H star compactly supported of M with QL bar coefficients, L not equal to P, realizes the local Langlands correspondences and the Jacquet-Langlands correspondence for GLHQP, at least the supracuspidal part. Cuspidal part. All right. And this is, and this is a bit of our motivation for trying to work out a semi-stable model for this M, because once you have one, you can actually compute what this thing is in terms of the components that you find inside of the reduction of that semi-stable model. And so I'll just say here that, next bullet point, that our goal is to find a formal model, which I'll call M hat, with semi-stable reduction. Okay. And since this M is actually this tower, it's not really clear what I mean by semi-stable reduction, but it will become clear by the end. Okay, so far so good? Excellent. Okay. All right, so as far as the geometry of this rigid space M goes, one of the first interesting bits of progress on it is the Gross-Hopkins period map. So there's a whole big theory of period mappings for Rappaport zinc spaces, but this is maybe the first very interesting example. So this next section is called the Gross-Hopkins period map. All right, the theorem goes as follows. 94. There exists a surjective étale map from M onto projective space of dimension h minus 1 over Cp. All right, so h, by the way, was this constant that was fixed in the definition of M. I just don't want to decorate M with too many things. So pH minus 1 of Cp, which is surjective and étale with Galois group just GLH of QP. So that is, M has an action of GLH QP, as we said before, and the quotient of it is just H minus 1 projective space. And so just take a moment to see how surprising this is. So, I mean, projective space ought to be simply connected, but here it is having this infinite degree étale map M, M mapping down to it. And then M itself is far from being simply connected also. It may have non-vanishing H1. So just a bit surprising that the projective space over Cp is far, far, far from being simply connected. Okay. All right, so where does this thing come from? And so I can give a very quick description of what this map is without showing any of its properties. And so this M was a space of deformations of a particular p-divisible group G naught. And so I'll just sketch this out. So given G naught, the p-divisible group over Fp bar. So we have the Dieudonné module. D of G naught, which is a module over the Witt vectors for Fp bar. And this is free of rank H. And then if I'll write over, continue over here, if G is a lift of G naught, have this kind of Hodge sequence. Where in the middle you have a kind of Dieudonné module for G, and so maybe G is over OCP. So I'll just put that G over OCP. And so this is a kind of stand-in for the first de Rham cohomology of G. And the Hodge sequence puts over here the differentials on G, and the quotient is the Lie algebra associated to the Cartier dual of G. And in this such scenario that we've had before, which is G naught is one-dimensional and of height h, then this is going to be one-dimensional, and this is going to be h minus one-dimensional. So this middle thing is going to be h-dimensional. And furthermore, so since G was a deformation of G naught, you have this iota map induces an isomorphism from the Dieudonné module of G, once you tensor up with OCP, to the Dieudonné module of G, it is G over OCP. Yeah, let's put it that way, over OCP. OK, yes, I know I realized I made an error because iota started out life as a quasi-isogeny. If it's a real isogeny, you get just a map like this. But if it's a quasi-isogeny, you're only going to get a map once you invert P. So pardon me, I'm just going to erase the O. OK. And then I'm going to invert P here. Tensor CP, all right. All right, so this deformation kind of gives us two pieces of data. One, you have this module with, which depends on G, but which comes with this filtration. And the other, this identification of this module once you invert P with this fixed thing, this fixed G naught. And so together, these two pieces of data, I mean, since we've got D of G naught, yeah, all right. So inside of, yeah, so inside of here, you've got this, we've got this line. And inside of here, let's just call the thing that pulls back just a fill, all right? Oh, OK, this arrow. And so what happens is that for every lifting, you get a line inside of D of G naught tensor CP, which is a vector space over CP of dimension h minus 1. And so this fill really lives inside of pk minus 1 of CP. All right. H, yeah, sorry, H. OK, thank you. All right, so to the deformation G, well, really to the pair G iota, you get this fill, this element, pH in projective space over CP. And so really what this does is it forgets about the alpha. And that's basically just like the operation of modding out by GLHQP, because any two alphas, remember alpha was the level structure, can be exchanged by an element of GLHP. So when you mod out by GLHP, you get this projective space. I didn't prove anything here. I mean, I didn't prove this was surjective or anything. But that's the story. All right, so that's the Gross-Hopkins period map. But to do the investigation of this semi-stable model, I needed a finer set of periods than just CP. I needed the Fontaine crystalline period ring. So the next thing to do is just kind of refine the Gross-Hopkins period map using the language of Fontaine's rings. And so, all right, any questions so far? Yeah, I'm doing pretty well. Right. OK, so this next section is called finite. Finite dimensional vector spaces with a capital D, a capital V, and a capital S. This is all right. So this is the language of Colmez, and so the starting point here is that CP is not big enough to contain the periods of the p-divisible groups that we'll be working with.
Now you can call them Banach-Kolmez spaces.
Banach-Kolmez spaces. All right, we have a convention. All right, so Banach-Kolmez spaces. All right. No, I sort of like. I don't, well, all right. OK. Yeah. What's that?
It's Fontaine's terminology.
It's Fontaine's. I see. All right. OK. So let's start with the ring A Cris. So this is a. P-adically complete W F-bar algebra. And just kind of tick down the properties that I need about it. So oh, it's flat. Sorry, it's flat over W of FP bar. And we've got this projection map from theta onto the ring of integers in CP. and it's continuous, and its kernel is a PD ideal, so it's got divided powers. So whenever x is in kernel theta, x to the n over n factorial is an acris as well. All right. And in fact, acris is like the universal, it's like the initial object in the category of rings with these properties. So it's properties. These. Oh, I should also say that it's nilpotent, topologically nilpotent PD ideal. Okay. So, all right. And then one more thing, we've got, well, besides the theta, there's another bit of structure, which is the phi. So phi from acris to acris is W of FP bar, semi-linear homomorphism. All right. All right, so that pins down acris. I guess I'll just continue on the next board. Okay. I'm going to need to invert P quite often, so the name for the ring you get when you take acris and invert P is Bcris plus, and I will have no need to remove the plus. So here we go. Bcris plus equals Cris adjoin 1 over P, so this is a very giant vector space over WFP bar when you invert P. And one very difficult thing is that it's it's impossible to kind of write down a random element of this in some unique or canonical manner. But what we're going to actually do is, in fact, periods of the spaces we're looking at, periods of the p-divisible groups don't just live in here. They live in a much smaller space. And they live in spaces where you take Bcris plus and you assign what phi does to it. So I'll just start with the fact, which is that the part of Bcris plus where phi equals 1 is just QP, as you would hope. And then if you pass to the next thing where, all right, so where the phi equals 1 part is just QP, but then the phi equals P part, so let's let U, Bcris, where phi equals P. And then this U, well, it's a vector space. Yeah, OK, so I'm going to, without, it'll be 1 where I put the, yeah, that 1 is there. This U, elements of it can actually be explicitly described. So this is a really large vector space over QP. And it's actually the set of sequences, x0, x1, and so forth, where the xn's live inside of OCP. And they're close to 1. So when you subtract 1, the thing has positive valuation. And each xn is the pth power of the one that came before it. OK, so this is, all right. So U is the set of such sequences. And now, this, as I've defined it, this thing is a QP vector space. So I have to tell you what addition is and what multiplication by an element of QP is. But these things are not so difficult. So if I have an xn, and I add a yn to it, so addition is multiplication. All right, addition is multiplication. Okay. And then if I have an a inside of zp, and I want to multiply by that, well, what else could it be? You just have to raise to the a, right? But it should be a, so this is well defined just because we've got this condition right here. The series converges. And then how does 1 over p work, xn? Well, it can be, I mean, to invert raising to the power of p, all you need to do is just shift 1 over. And so I can just write this way, xn minus 1. No, xn plus 1. OK, shift over to the left. OK. All right, so this is actually a QP vector space, and this is what we call U. And I have to tell you what this theta does to it. I mean, theta takes Bcris into CP. And so what does theta do to such a sequence xn? So theta of the sequence xn is log of x naught. And this makes sense, again, because x naught is close to 1. So putting all this together, so note that if x naught is actually 1, well, you get an element like t, which is 1 zeta p squared, and so forth. And this is in kernel of theta. And kernel of theta is none other than, this is very easy to see, it's just the line generated by t. Okay. So, did I mess up? Yeah, because it's like that. And then u sits inside of an exact sequence, which Colmez calls the fundamental exact sequence, where u maps via theta to c, to 0, and then the kernel is cp, and then the kernel is qpt. Okay. So we've got a very large qp vector space. It's got this line inside of it, and the quotient is cp. And so this thing is of, all right, in Colmez's terminology, this is of dimension 1, 1. This 1 refers to this being one-dimensional. This 1 refers to this being one-dimensional. Okay. That's great. I should also mention what happens when instead of this u, we take, instead of u1, we take un. Or I should say just to be consistent with what's about to happen. So also admits, which is b cris plus phi to the n equals p, also admits an explicit description in terms of, I knew this would screw me up if I changed n stages. All right, is like this, and this also admits an explicit description, although for this it's best to kind of shift everything by 1 so that multiplication becomes addition. And then these pth power maps become not pth power maps, but multiplication by p in the Lubin-Tate formal group attached to the unramified extension qph over qp. So this still admits an explicit description. And then it sits also inside of an exact sequence. Maps to cp, same theta, to 0, except this theta has to be described in a different way. It's the formal, not logarithm, but rather the formal logarithm attached to the Lubin-Tate formal group, again for this guy. And then the kernel is also, well, it's not one-dimensional anymore. It's qp to the h times, I'll call it th. So if t is like a, I forgot to say it. T is like the p-adic version of 2 pi I, and it better be because it's the kernel of a logarithm map. And this t is like a period of the formal group GM, whereas this th is the period of the Lubin-Tate formal group. Zp to the h module of dimension 1. Okay. All right, very good. Okay, so this can all be generalized to that situation. And now, all right, so soon I'm going to relate these Banach-Colmez spaces to the Lubin-Tate formal group. But just before that, I want to give you a taste of what's to come. Oh, yes. Oh, yes. Yeah, this is, yes, qp to the h is the Witt vectors of f p to the h when you invert p. Yeah. This sits naturally inside of w of f p bar when you invert p. Okay. Yes, and yes, it makes sense you can multiply there because these guys commute with phi to the h. Okay. All right. Right. Oh, I probably shouldn't have erased that. But one minor point I want to make is that you can find pieces of this vector space U, this giant vector space U. So remember, I'll just write it again. X naught, x1, and so forth, where xn to the p is xn minus 1, and they're close to 1. But if I let inside of this, if I say U upper 0 is the set of all sequences xn, where the valuation of the first element of the sequence, the x naught minus 1, if it's below this key number p over p minus 1, all right, so I'm just taking kind of like a subspace of this giant U thing. It's no longer a vector space when I impose this condition. All right, so this is automatic just because x naught has to be equal to 1, but this is not. And doing this actually forces the evaluation of xn minus 1 to be exactly 1 over p to the n minus 1 times p minus 1 by some kind of Newton polygon argument. I mean, as soon as you restrict the valuation to be less than this key number, the Newton polygon never has a break in determining what the valuation of the next guy is, and the next guy, and the next guy, and so forth. And so just as like you can give this kind of analytic space structure on this U naught. So I can define like a formal scheme, U hat naught, to be the SPUF of a direct limit of rings OCP, double brackets a yn, so maybe yn will be this guy. Just less than. Just less than. I want. Oh, God. That's really terrible. Thank you. Thank you, everybody. All right. So yes, indeed, less than. So just kind of the nth truncation of this space of sequences can be written down using this formal scheme, yn zn, where yn times zn is supposed to equal p to the that, p minus 1, right? And then these transition maps are given by whatever they have to be. But modulo the maximal ideal of OCP, it's basically just yn goes to yn to the p, zn goes to zn to the p. And so this formal scheme that I've written down, it's a model for U upper naught for this part, in the sense that its OCP points are just U upper naught. And the reduction, all right, yeah, OK, FP bar is the spec of this direct limit of fp bar adjoin y and a z modulo just yz. But now what do I have to do to it? I have to just keep on taking pth roots of these guys. So I get an object. I don't know. I mean, I don't want to clash with Peter's talk, but I'm going to I'll call it the perfection, right? I mean, I take pth roots of all of the elements, and I'm just going to take the direct limit of rings along the Frobenius maps. And so this sort of ring, I mean, without the perfection, this is like the local ring at a node. But with the perfection, it's sort of what you would expect a semi-stable model for a tower of curves to look like. The nodal singularity has a local ring which looks like this. Okay. All right, so that was just a little reflection. I'm not actually going to use this. But yeah, so now I can return to this bit about p-divisible groups. Yeah, great. Oops. Yeah, this resists you, doesn't it? Okay. All right, so back to this, yeah, divisible groups. All right, so this next section will be called crystalline period maps. Period maps, and everything I say in it will have already been written down by Farg and also anticipated by faulting. So I guess Farg après faultings. OK. And so let's suppose we've got a triple like we had before, so a G, an iota, and an alpha, where I'll remind you everything. So G is a p-divisible group, formal of dimension 1. And then iota identifies G naught O mod P with the G tensor O mod P. It's a quasi-isogeny. And then alpha, yeah, I'll get this right this time, QP to the H it's an isomorphism of QP to the H. It's a basis for the Tate module, VP of G. All right, and so the thing here is that we want to construct a period map from this VP of G into something else. Now, what is that something else? I mean, it's going to be something crystalline in nature. And well, before writing it down, let's just go to the margins over here. And I'll motivate by saying that if A over C is an abelian variety, then we've got a map that's like a period map from H1 of A with Q coefficients and to H1 de Rham of A over C dual, right? I mean, a cycle just gives you a way of evaluating them. It's just an integration map. And so this C is kind of big enough to contain all the periods of this A. But over here, oh yeah, and this is like a Tate, and then when you tensor this with QL, you get like with QP, you get the Tate module, right? Okay, so you get to map from TP of A into something like H1 de Rham dual. And then over here, we're going to do something quite similar. We're going to take the rational Tate module, and it turns out it always maps into, all right, so this D of G is something called the messing crystal for the p-divisible group G, and it can be evaluated on PD thickenings of OCP. So we're just going to do it on this particular PD thickening. And yes, so since it was rational, I have got to invert 1 over p. And then Faltings proves that this is an isomorphism when you pass to phi equals p. Okay. What? Yeah. Yeah, see, I have trouble with, OK, so maybe I'd better add his name, but I should hope that his spirit pervades everything I do in this section, OK. OK, right. Yes, I think so, just because P is, everything is formal and connected. There are a whole bunch of theorems that say, you know, the messing crystal does this and this for all P, but when P equals 2, you have to assume G is connected, but G here is, so I think it is actually OK. All right, so this is actually an isomorphism. And now, since we've got this iota, we can compare the messing crystal for G to the messing crystal for G naught. And because the crystal has this, well, crystalline nature, this thing is isomorphic via alpha lower star. This is OK. It's covariant, by the way. I should have mentioned that, really. To D of G naught. What? Oh, thank you. Yeah, thank you. OK. So D of G naught, tensor B plus Chris, yeah, phi equals P. All right. And on the other hand, we've got this, so we're just kind of comparing what we get, the data that we get out of iota to the data that we get out of alpha. So I have to, I guess, take alpha inverse, sure, to QP to the H. This maps over here. Because it's just the way that this VP of G works. It's like Hams from QP over ZP into the G. And then when we apply the crystal to both of these, the crystal here has phi equal to P. And so that's why the crystal has this, yeah, in the Ham, you get phi equal to P also. Yeah, good. All right, and now, so each triple gives you H elements, like a basis for this vector space. But this D of G naught, it's very easily computed what it is as a phi module. Phi to the H on this D of G naught just equals P. And this is not so difficult. But in fact, this is the same as B. I mean, once you choose some kind of basis, this is phi to the H equals P. Phi to the H equals P. And this is the Banach-Kolmez space that we were calling UH from before.
Then you have to make the isomorphism. So QP to the H cannot be isomorphic to Chris plus.
Oh God, I'm sorry. Right. So, yes. I'm sorry. So this just maps. It just maps in. It's not an isomorphism. Yes. Okay. It just maps in. Yeah. Thank you. All right. So for every deformation like this, you get H elements inside of U to the H. And so this is going to be the basis for a period mapping, which is more primitive than the Gross-Hopkins period map. And so I'll draw the appropriate diagram, right? All right, so a few boards ago, I mentioned the Gross-Hopkins period map. And that was M Lubin-Tate maps down to pH minus 1. And what I've just written is a map. It happens to be an injection. See, I meant to write an injection there, not an isomorphism. Into U sub H, direct some H times, right? I mean, there's a basis vector here. So where did they go? You get H elements of U to the H. And you trace through everything that Fargs writes down. And so this maps down to H by H matrices over CP. And what is this? So if I've got a vector or an H tuple of vectors living in UH, this, I need to get a matrix out of it. And the matrix is going to be the matrix you get when you take theta and you plug in phi to the j, or phi to the I of uj. I and j both going from, oh no, I better write it down. H minus 1 to h. There we go. OK, and so the theorem of Farg's is that this maps down to here, but when you follow it all the way down here, you can never get a matrix of full rank. And that has to do with the filtration that comes from d of g0. Something has to be respected. And it actually lands in mh of Cp, where the rank is equal to h minus 1, no more, no less. So this is in here. And this square right here is Cartesian. I don't know if there's a symbol I can use to denote that for a square I write on the board. But, and now I can complete the final arrow. If I've got a h by h matrix of elements of Cp, and I tell you it's rank h minus 1, the columns of it generate a subspace of dimension h minus 1. And that's this map down here. And so when I say there's a period map that's more primitive than the Gross-Hopkins map, I mean this. I've sort of interceded something here. OK. All right. So this is a complete description of the Lubin-Tate moduli space in terms of these vector spaces UH, which I said were not too difficult to analyze, together with some kind of condition on what rank, what happens when you apply theta and you get you determine what the rank is. And I'll just say that I'll just kind of make an aside here that in h equals 2, how does this play out? Well, if I've got a two-tuple, a pair of vectors v1, v2, and I tell you that this matrix ends up being singular when I apply theta to it, it's going to mean that when I take the element v1, phi of v1, v2, minus v1, phi of v2, so v1 and v2 both have the property when you hit them with phi twice, you get p. And then it turns out that when you just hit this with phi once, you get negative p times what you started. And so this lives in, just write it u1, where epsilon has this property. It just lives in vit vectors of fp squared. And also, when you hit this whole thing with theta, it has to be 0. So it has to actually live in the kernel of theta, and this is just epsilon t times qp. All right, so that's some extremely severe condition on what all these v1 and this v2 has to be. All right, so now, yeah, in the last 12 minutes, let's sketch out what the stable reduction of M looks like in the case of h equals 2. It uses this whole picture as a starting point. Okay. All right. One thing I have to get out of the way is that among the p-divisible groups inside of MLT, inside of M, inside of the Lubin-Tate tower, some of them are CM, which means that they have complex multiplication by a quadratic extension of QP. All right, so this is all the situation of h equals 2 now. Okay. And so the theorem is as follows. I have to remove the CM points from M to do this analysis. The singularities are very highly concentrated at the CM points. And you have to blow up at them over and over again. So I'm just going to remove them, and I'm going to say that this has a formal model M hat over OCP such that the special fiber has singularities with local rings fp double brackets x comma y mod xy, and you take the perfection of this. This is the ring we encountered earlier. So this describes the singularities of m hat, and then what are the irreducible components? Has irreducible components of the form C perfected, where C over Fp bar is the projective smooth curve, and there are 4 possibilities for it. So let me just switch these things. Okay. All right, so M hat tensor Fp, oh, there should be a bar there, sorry. Has irreducible components of the form C perfected. What does C perfected mean? C is a curve over Fp bar. You take the inverse limit along all the geometric Frobenius maps, and you get C perf, right? And so what could C be? There are 4 possibilities. One is the curve x to y to the p minus x to the p y equals 1. Another is y to the p minus y equals x to the p plus 1. Another is y to the p minus y equals x squared. And the other is it's just p1. And so those 4 are the only ones appearing, and I forgot to mention that p was odd. Now p is odd. Now p is odd, OK. And I'll make a few remarks about this. You can see where this might come about, where a curve of this form might come about, because it's rather in here. I mean, v1 and v2 are living in this space of sequences. It turns out you can just scale the first element of the sequence, and you're left with something like v1 to the p, v2 minus v1, v2 to the p equals something manageable. All right. The second come out, I mean, these guys come out during computations in the wild part of these of this space. So the best I can do is sketch out a little bit more of the structure of this m tilde, right? No, m hat. OK. All right, I've got 10 minutes. That's perfect. So let's say the gamma is the dual graph of the special fiber. So vertices are components. So vertices correspond to components CV, where CV is one of the 4 curves here. And edges correspond to singular points. So two vertices meet at an edge if the CV and the CW meet at a singular point. OK? And so I'm going to, well, yeah, now I wonder whether I should first draw the picture and then explain or what. But yeah, I'm going to need, definitely need a whole board for this. All right. So it's OK if I write on this backboard? Is that all right? Yeah. It's kind of the last thing I'm going to do. Ah, yeah, I need to write like kind of a guide. So A, B, C, P. OK. So I have like a pretty picture. I have slides for this, but they're on my website. I'm just going to draw this all out. So the A curves arrange themselves in the Brouhat-Titz tree for PGL2 QP. So here I'm going to draw the situation of P equals 3. So it's an infinite graph of degree 4. A, and so forth. And where do these B curves come out of? So I'm going to take this center guy and draw something coming out of it. But the implicit understanding is something very similar comes out of all of the A vertices. And so out of the A vertex comes, well, many B vertices. This is, OK. B, 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 B. And so forth. Similarly coming out of A, all these B vertices. And then out of, now if I kind of take this graph and subdivide it, and place a P at each subdivision, then curves of C-type come out of it, followed by curves of P-type, followed by curves of C-type, followed by curves of P-type, and so forth. Okay. All right, so what is going on here? I can sort of, yes?
You're looking at the smooth direct model.
Yes, so what I wrote, so I covered it up, but it did write.
Then aren't A and B going to be isomorphic?
Yeah, they're going to be isomorphic, so why have I labeled them different ways, right? And my justification for doing that is that this whole picture has an action by, well, GL2QP. And what ends up happening is that the actions on the A curve and the B curve are drastically different. The action, so GL2QP, the stabilizer in GL2QP of this A is it's SL2ZP. Maps into aught of the A curve. And that action, well, what is it like? You can imagine it. The matrix takes x comma y to what you hope a matrix would do to a pair x comma y. That preserves that curve. And there's a large tame part of the subgroup. It factors through something with a large tame part. Whereas in the situation of B, the stabilizer, whatever it is, I'll call it gamma, and this factors through a pro-P quotient of gamma. And so that's my justification for labeling them different things. And then I also should remark that when you carry this out for GLH, when H is larger, A and B really do become different things. Okay, and that's the C, and that's the P. And then, you know what? Maybe I'll just take questions now. If whatever you want me to explain, I shall. I'll just leave it up to you what you want me to explain. So, 5 minutes. Let's take questions. Let's do it. Okay.
Did you finish the picture of what have to do?
More C's. P's and C's alternating forever. These are, it sort of has to do with the fact that.
And it's 3 coming out each time.
No, that's just artist's conception. There's in fact, oh wait, no, I think it is actually P, lowercase p, in which case, yes, 3. Yes. Okay, got it. I didn't mean to do that, though. This is all wrong. It's sort of P cubed each time. I just didn't feel like drawing 27 B's coming out of each one. Yeah. Yes?
What are the curves when H is greater than 2?
They're not curves anymore.
Oh, sorry. Okay.
So when H is greater than 2, my understanding is still incomplete when H is greater than 2, but I can tell you what the A and the B are going to turn out to be. So when H is greater than, when H is anything, the A ends up being the following thing. You could kind of read it off. It's very similar. So this, where I goes from 1 to H, and J goes from 0 to H minus 1. That's the A. The B, I'll write it when H equals 3. It's determinant of, okay, 0, 1, x1 to the p, x2 to the p, 0, 1, x1 to the b squared. Okay, it's a surface in it's a surface. So when you scale this down by 2, you get something disconnected, but each component is like the b over there. They really are different. Okay.
But you still have only 4 kinds?
No, I don't know. I don't want to. I don't know. I think that it's bounded. I think that it's bounded based on, but I don't know quite what the bound is. I would guess, though, my strong guess is that when H is greater than P, you don't have any problems that H is too small, then you still just get 4 kinds. Yeah. Yes.
So can you say if we take a
chief on M, and then we start taking nearby cycles on here.
Mm-hmm.
So
Oh,
you
yeah.
get something in each node. What do you get?
Oh, yeah, yeah. So this is one of the things I was hoping would be asked. And see, I could explain different things, but I'll just have it be democratically. Oh, now I have to cover. That's okay. Okay. All right. Okay. Yes, there is a vanishing cycle sequence that relates the cohomology of M to the cohomology of this everything on this graph. And what happens is that H1 of M with QL bar coefficients, the supercuspidal part, ends up being simply a direct sum of what comes from the nodes. So V in the graph gamma of H1 of CV QL bar. And so it's really CV perfected, but the CV and its perfected thing have the same étal site. So it's really just the same thing. It's just writing CV. And so this is so this is really, so all the supercuspidals are found somewhere in this direct sum. And in fact, it partitions all of the supercuspidals in terms of orbits for G cross J of something induced from KV to G cross J of an H1 of the CV like this. So maybe KV is the stabilizer of CV and G cross J. And this picture interfaces very well with the theory of types of Bushnell-Kutzko. You can write everything down explicitly.
So in that case, why should you expect there to be only 4 different times when H is bigger than P?
Well, because the nature of the action of this on this is quite simple. And also in this theory of types, the representations that you get, that you start with to construct the supercuspidals are also very simple. Most of them are just characters. So,
The different extensions of degree H.
oh yeah, there are different extensions. That's why there are many vertices. You see, we saw the same isomorphism type appearing infinitely often, maybe type B or whatever. But the B appears in different places. And this B gives you representations that have conductor P to the 7th. But this one gives you representations of conductor P to the 8th. It just so happens that the B's are isomorphic as curves. The actions on them by the groups are quite different.
So the A's always just giving depth 0.
Yeah. The A's always give you depth 0 representations.
So they're stabilized. So when you had the gamma was stabilized with B, this gamma these gammas to gammas have V somehow. This gamma depends on the.
Gam.
I mean, there's some notation where momentarily something maybe
Yeah. All right. I'll lift it up. Over here. Yes. Yes. This.
Depends on.
Make this. Make that over there. I mean, in general, it's like this. If KV is the stabilizer of V in G cross J, then of course you have an action of KV on CV, and then of course KV will act on the H1s, and then when you induce all the way up, you'll get some family of supercuspidals that appear there. They all have the same depth. The A's all give you the depth 0, guys.
Do you get some more complicated picture of P as 2?
When P is 2, I haven't done the computation completely, but I think that what happens is that y squared minus y equals x to the 2 plus 1. That's OK. That's an elliptic curve. But the one that was the C curve, this is no good anymore. And I think you have to replace this with also x cubed. I think the B and the C become the same thing. That's my guess for what happens. You certainly couldn't have a conic like this, because then you wouldn't see any cohomology anymore. I think it must be like that.
What about the CM product
They're at infinity. So this graph has two kinds of ends. Some of the ends just go by from following the depth, this Bruhat-Titz tree. Not those. Those corresponds to really the boundary of the Lubin-Tate space. The CM points are exactly the ends that arise from going out here to infinity. And so there are like two kinds of ends. I'm really, OK. The last thing maybe I should say is that the ends of this graph are like P1 of QP, disjoint union, and this sort of accounts for the Steinberg, by the way. The Steinberg representations appear here. And then the disjoint union of all the CM points. OK. Yes?
I mean, at the beginning
Yes.
Is there any relationship between this picture and the pictures of stable reductions?
Oh, absolutely.
So can you say something about what the relationship is?
Yes, absolutely. Yes, that was another thing I was hoping someone would ask, which is that. All right, back. But is it okay? I mean, I'm already over time. Maybe if it's, I can't. What? You're the host. You got okay. I don't know. Okay, there's a procedure for passing from this stable model to the semi-stable model for any particular modular